again, we're doing chapter 1. The first part we introduce bunch of, this is about kinematics, how to describe a motion. The first part we introduce bunch of quantities to describe motion. They are mostly vectors, like mostly these three quantities: displacement, velocity, and acceleration. They're organized like this. And then starting from chapter 2, we talk about, we did some example, and then we start from, starting from part 2, we talk about some specific kind of motions. Which, first of all, we talk about constant velocity motion. That's not much to talk about. And then talk about constant acceleration motion. And that's the most important thing for us. And we gave 4 formulas, 4 kinematic formulas for constant acceleration, okay? Like showing up here, okay? And then we start to solve some, we discuss like qualitative behavior, and we solve the problem quantitatively. And then we talk about the specific kind of motion, which is free fall, okay? And we kind of explain that why you drop 2 objects, different weight, from same height, same time, they're gonna hit the ground at the same time. You can explain everything by using the formula for constant acceleration. That's the simplest possible explanation for these, okay? And then if you measure the free fall acceleration, you got 9.8 meter per second squared. That's a kind of like universal number. And then we don't know where this number come from yet. We'll talk about that in chapter 4. So the example I want to talk about is, okay, free falling objects, okay. Let's do example 2.8, okay. Now there are multi-part of this example, and we'll do, it's either totally 5 different parts. We'll only do a few first few parts, and then we'll do the rest, okay. So, so this case, you have a ball is thrown from the top of a building, okay, like right here, with initial velocity 20 meter per second, straight upward, okay, through upward like this, okay. Now the ball just missed the ball just misses the edge of the roof on its way down as shown. So basically it means that it goes up. When it goes down, it does not fall back to the top, but it goes all the way down, to the ground, okay. And so you're given some information here. First of all, you got this height, which is 50. You also got 20 meter per second as your initial velocity, and that's all you got. Okay, now these things here are, I think, after you solve the problem, you get it. Okay, so you don't get much of that. So let's start from drawing the picture and try to solve the problem. Okay, and then we'll come back for the unknowns. Okay, so this is the example 2.8. So basically, we're doing it for free fall motion, okay? So basically, again, you should always start from drawing a picture, okay? So a ball is throwing upward like this, like a ball. So you imagine it's gonna go all the way to the top and then falls back down, right? Now, two pieces of information are given. First of all, the initial height is 50 meter. Secondly, the initial velocity going upward is 20. Hold on, let me double check. Yeah, 20, okay. 20 meter, okay. Per second, okay. Now, what do we want to solve for? So we want to solve for the time it needs to reach the maximum height. So this time, okay. And then we want to solve for maximum height, and then time needed for the ball to return to the height from which is thrown, and then the time needed for the ball to reach the ground, okay, and the velocity when the ball is at 5 seconds. So A is time to the maximum height. And B is the maximum height itself, how high it can go. And then C is the time to come back to the, is that right? The time needed to return, okay? Okay. Time to return. Okay. And D is the time to go to the ground. Okay. Time to go to ground. Okay. And then E is the velocity at t equal to 5 seconds. Okay. So assuming you start from this at t equal to 0. So these are the 5 questions we want to answer for this question, for this problem. Okay. Okay. What I want to say here is, okay, free fall problem is essentially just a constant acceleration motion problem. So all we talk about on constant acceleration motion still apply here. So basically we have these 4 formulas and we need to choose one formula to use. Okay. So what's special about free fall is this. Okay. Remember when you have a free fall, the acceleration is always going downward with a magnitude of 9.8 meter per second squared. Okay. So I still use A for the acceleration, okay? And then that equals 9.8. So that's something it didn't mention in the problem at all. But as far as you see that as a free fall motion, you should realize this is some condition that's given. This is something you know. Well, if you don't realize it, certainly there's no way to solve the problem. You have to realize this is a free fall motion, the acceleration is 9.8, okay? And that's one thing is special. Now, another thing special, especially for these kind of problem that this object goes up and then goes back down. It's very important that you set up a coordinate system carefully, because there are going to be quantities that's positive and quantities are negative. You don't set up the coordinate system, then you don't really know, and then you get confused and you may get some wrong answers. So now you can easily define this as your origin of the coordinate system. That's because that's where the ball starts from. However, you have to decide which direction is positive for you. Okay, well, you could actually choose the upward being positive or downward being positive. Okay, either one is fine, but you need to be consistent with your choice. Okay, so for this one, let's choose this as our positive direction. Okay, so we will say this is our positive direction. This is a one-dimensional motion, so this is positive. Anything going upward is positive, and corresponding anything going downward is negative. So if you say if this is defined, so the acceleration actually is negative 9.8. Okay, it is negative because the acceleration going down. Okay, well, our positive direction going up. Well, the initial velocity here is positive. Okay, again, this is very important. If you don't put the minus sign here, if you say both of them are positive, you get some terrible answer, crazy answers, as we will show. Okay, anyway, and what about this 50 meter here? So that's basically your total displacement when it goes from initial position all the way down to the ground. Okay, see in these questions, okay, there are 2 kinds of questions. I mean, there's 3 kind of motions you're talking about. Actually 4. Okay, one is the first kind of motion, like see A and B. It's interesting in the motion going from here to the maximum height. So that's kind of one motion. Well, for C, it asks you time for return. So it's interesting that the motion starting from here all the way back to here. That's another motion, right? Those 2 are different. And then the D here, times go to ground. So it's a motion starting from here all the way to here. And finally, E is the motion that start from here and end up at 5 seconds. So all these motions are a little bit different. They're part of the same motion in some sense, but when you solve different part of the problem, you need to focus on the specific motion you're talking about. Okay, so let's start from A and B because they care about same kind of motion. Okay, so this part, so what you can do here is, okay, if you let's just for A and B. Okay, let me write everything down again. Okay, so you have this x here, right? And you're given VI equals to 20 meter per second. Okay, and then you know acceleration is negative 9.8 meter per second squared. Okay. Now this 50 meter is not useful, very useful here because you're not interested in going downward like that. Okay. Now, well, when you're mostly interested in the displacement going from here to maximum height. Okay, let's say somewhere here. Okay. Now there is another piece of information that's actually given when it says when it asks you something about maximum height. Okay, and that piece of information is critical for solving any problems like this, involving maximum height. Okay, what is this critical information? So when they ask you something about starting from here to maximum height, what do you know besides these two, besides the initial velocity and acceleration? What do we know? What does it mean to go to the maximum height? What is the condition? What is the physical condition, or what this thing go to the maximum height?
The velocity becomes zero.
Yeah, exactly. The velocity is zero, right? So for this A and B part, we know VF equals zero. Okay. Again, that's kind of critical. If you not say it explicitly in the problem, it will just ask you something goes to maximum height, but you need to read out because this is the maximum height. That means the velocity is zero. Because if the velocity is not zero, it's going to continue rise. Okay. Only when velocity is zero, it reaches a maximum height. So this is another piece of information. So we got the three pieces of information here. Okay. Now, what do we want to find out? We want to find out the time and then the maximum height itself. So essentially, we need to find out delta t and delta x. Now, again, remember we got these four formulas. Let me list them here. For constant acceleration motion, or we call it kinematic formulas. Well, they can be written as different ways, but I'm just writing it like one way, okay? Okay, these are our four formulas, okay, that we can use. Now, which one should we use to solve, let's say, delta t? Let's start from delta t, okay? Or we can, okay, yeah, let's start from delta t. Which one do you think, send me a message. Which one do you think we can use to solve delta t? Out of these four formulas, and given those three pieces of information. Okay, I got some messages. Let's see. Yeah, okay. I got different answers. Some people saying Formula 1, and some people saying Formula 2. Let's see Formula 1, okay? In the Formula 1, there's definitely delta T here, so that's something we want to know. And then there VI, VF, and A. They're all given, so definitely Formula 1 is good, okay, to use. What about Formula 2? There's definitely V and VF here that's given, but delta T and delta X, there are two unknowns in Formula 2, so that's not the good one to use to start from, because there are two unknowns. You don't know which how to solve two unknowns with one equation. So let's use a Formula 1, okay? So again, as I said, you can plug in numbers right away, but I always manipulate the formula first, okay? So it's your choice. But I kind of hope you guys can develop this habit of doing the manipulation first. Okay, so if you move the VI to the left, you have VF minus VI equal to A delta T. So divide by A then. So I have delta T equal to VF minus VI divided by A, okay? And then you just plug in numbers. So VF equal to 0 and VI equal to 20 meters per second. And then A equal to negative 9.8 meters per second squared, okay? So in doing this calculation, you see the two minus sign cancel out. So what is left is 20 divided by 9.8, okay? So you got 2.04. And then unit here is meter per second divided meter per second squared, so that gives you a second, okay? So it takes 2.04 seconds to go from here all the way to the top, okay? Now, one thing you notice here is this negative sign here is critical. Without the minus sign here, if you say acceleration is positive, okay, then according to this, you get a negative 2.04 seconds, which is certainly meaningless, right? You certainly don't expect anything happen in negative time, right? In negative time interval, that's meaningless, right? And that tells you how critical it is to specify the sign correctly, and that's certainly related to the way we define our coordinate system. Now, as I said, it doesn't matter which way you define as a coordinate system. If you define it as the positive direction going downward, your acceleration would be positive, but your velocity will be negative. And then still, so this is gonna be like plus, and this will be plus. So you still get a positive time. So it doesn't matter which direction you define as your positive direction, but you need to be consistent with your definition, and you need to be specify the sign for the quantities correctly. Again, remember they are vectors, you know, so there's signs associated with them. Okay, so okay, we got delta t. Okay, let's talk about delta x then. Okay, so which formula after we got our delta t, which formula you think we can use to solve for delta x? Again, send me a message. Okay, yeah. Actually, yeah, some people saying 2 and some people saying 3. Actually, this one, after we got delta t, this one definitely can work because now we know delta t, vi, and vf, we can go delta x. This one works as well because we know vi, delta t, and a. So we can solve for, actually the fourth one works as well because we know, actually the first one we can use even without knowing delta t because we're given the velocities and acceleration. So all these three formulas actually can work, okay? So you have a lot of choices here. So, and for people who hate the squares, let's use the second one, okay? Let's say delta x equals to vi plus vf divided by 2 times delta t, okay? So from there you got vi 20 meter per second and the vf 0 and divided by 2 times delta t, which is 2.04 second, okay? So it's 20 divided by 2 is 10 times 2.04, so it's a 20.4, okay? Meter per second times second, you got meter, so the unit is right. So you got 20.4 meter, okay? But that's actually not exactly what is asked. What is asked here is the maximum height. So what we're calculating here is only the displacement, okay, from the initial position to the height. So you have to count 50 meter as well. So the maximum height is actually 50 plus 20.4. So that's 70.4 meter, okay, for the maximum height. That makes sense to you guys? Okay, so let's talk about part C now, okay? Now I'm gonna, after part C, I'm gonna leave the last part for you guys, okay, to calculate. So let's try to calculate part C. Part C asks you the time to return. Okay, now for this one, we're looking at a little bit different motion. The motion we're interested in now is that this thing goes up all the way to the top and then comes back, okay, to the same position here, okay? So that's the motion we're interested in. So for example, in the previous one, we're saying v of f equals 0 because we reached the maximum height, right? Well, for now, it is not 0 anymore because this is definitely moving at this point. When it reaches the initial position here, it's still moving. So we don't know vf anymore, okay? So what we know here though is still like this, vi equals to 20 meter per second, and then acceleration is still negative 9.8 meter per second squared, okay? Now we still define this as our positive direction. So we want to know the time it takes to for this to happen, to return to. So we're interested in the total time here, okay? Now there are two ways to get it. First of all, you can just try to figure out the whole time here, okay? Second of all, since we already figured out the time it goes up, so you can for some reason figure out the time it goes down. That works as well, okay? But certainly with only two pieces of information, we cannot get it. See, all these formulas we have, they all involve 4 quantities, okay? Knowing only 2 of them, we cannot solve another one, okay? We need to know 3 of them to get another one, okay? So while we only have 2 here, okay? Again, there is a hidden piece of information that we need to figure out, okay? And can anybody try to tell me what is another piece of information that we do know and that we can use to solve the problem? It's not, I mean, it's a little bit tricky, but it's, again, the only thing we have, right? See, it's possible we have a VF, VI, A, delta T, and delta X. These are the kind of like the 5 quantities we have. So, okay, I got a message here. Let's see. Okay, great. Somebody got figured out. Good. Anybody else? Okay. Yeah, it's not that trivial. So the actually the another piece of information we do know for this whole motion is delta x actually is 0, okay? The displacement is 0 because it come back to the same height, you know? Again, that's kind of a little bit hard to figure out, but we only have this 5 pieces of information, right? So we don't know delta t, right? So that's we don't know, and we don't know VF as I said. So we know V and A. So the only one that in there is delta x. So, and if you think a little bit, you can see that delta x is 0. Okay. So now, given the 3 pieces of information, VI, A, and delta x, which one should we use to figure out delta t? Again, send me a message. Which formula should we use to figure out delta t, given delta x, A, and VI? Anybody? I mean, just send me a message. Okay. Okay. I got 3 messages. Okay. Okay. Okay, great. Okay, the correct answer is the 3rd one. Okay, this one's the one to use. Okay. Now somebody said 2, but 2. The problem with 2 is we don't really know VF. Okay. As I said, we don't know VF. We know VI. We know delta x. We know delta t. But sorry, we're looking for delta t. We know delta x and VI, but we don't know VF. So there's gonna be 2 unknowns here. Okay. Same thing for this one. This one does not even have. Yeah, we don't know VF, so we cannot use it. So the 3rd one actually is the one to use. Okay. Well, this one is a quadratic, which is a little bit hard, but let me set it up. Okay, but there's a way out of it. Okay, so let's write down that one. Okay, so we have delta x equals to vi delta t plus 1/2 a delta t squared. Okay, now it seems like complicated because the quadratic there's a quadratic term here, but the good thing is delta x is 0, right? So you don't really need to know the quadratic formula. So you actually have 0 here. Okay, and vi delta t plus 1/2 a delta t squared. Okay, now you can factorize out delta t. So you got vi plus 1/2 a delta t. Okay, so this whole thing equals 0. Okay, well, in order to satisfy this equation, there are 2 possibilities. One is delta t itself is 0, or this combination here is 0. Okay, or vi plus 1/2 a delta t is 0. So these corresponding to the 2 roots of this equation. Well, this root certainly is a trivial root. We don't need that one. So that's not the interesting one for us. This one is the one that's interesting. So from this one, you get delta t equals to negative 2vi divided by a. Okay, so plug in numbers, you have negative 2 times 20 meter per second divided by negative 9.8 meter per second squared. Okay. Now notice again, the minus sign here is important because this cancels this negative sign. Okay. So you have 40 divided by 9.8. Okay. And you got 4.08 meter. Sorry, this is gonna be like second. Okay. Because meter per second divided by meter per second squared is second. So 4.08 second is the answer for this problem. Okay. Now, actually, you see something interesting here. Okay, so based on what we saw from the first part, okay, we got 2.04 second. It takes this much time to go from here all the way up to the top. Now we see that the total time it takes to go from here all the way back is 4.08. That means the second part of the motion takes exactly the same time. So it takes same amount of time to go up, 2.04, and then it takes another same amount of time to go down, 2.04. Okay, so that's kind of, in some sense, this motion is kind of symmetric. Okay, and actually you can solve for VF in this case. Okay, although it's not us, let's do that. Okay, let's use the first formula here. VF equal to VI plus A delta T, right? So VI is 20 meter per second minus 9.8 meter per second square times 4.08 second. Okay, if you do this calculation, you see that. Okay, let me do this calculation. Okay. Wait, yeah, you got actually negative 19.98 meter per second. Okay. Now, if for the rounding thing, if you rounded up is basically 20 meters per second. So what you see here is the final velocity when it goes back to the same height, have the same magnitude as the initial velocity, 20. It's just going to a different direction. So you have VF going up, sorry, VI going up and VF going down, okay? And they have same magnitude, just going opposite direction, okay? So again, this motion is kind of symmetric, okay? There's a reason for that, but that reason is pretty deep. We will talk about the reason in chapter 5, I think. Yeah, so for now, you just need to understand this motion, this free fall going up and throwing something upward, okay, going up and coming back down. It's kind of symmetric, okay? It takes same amount of time to go up and same amount of time to go down. And then their velocities are pretty much the same except for the sign, okay? Okay, so let me show you another way of solving this same problem just because I can, you know, or maybe it can help you to understand it better. So as I said, another way to do that is if you, since you already know this this part of the motion, how much time it takes. So to get the total time, you just figure out the time it takes to go down, right? So let's think about that, okay? So this is the part that goes down, right? So I'm going to define my positive direction going down like this, okay? Just to because this is a little more convenient, okay? By this using this definition here, right? For this motion here, we have VI equal to 0, right? Because this is where to start from at the height. Okay, so this is the second method two, okay? And then the expression now is a positive 9.8 meter per second squared, right? Now we don't know VF certainly, and we're trying to figure out delta T, but we know delta X, right? That's the same displacement we calculate here. That's 20.4. So, and since we define this as our positive direction, so this is a positive 20.4 here, okay? So we have these three pieces of information. From there, we can solve for delta T. And again, the formula to use would be the third one again, okay? So we have delta X equals to VI delta T plus 1/2 A delta T squared. Well, the good thing is this term here is 0 because VI is 0, right? So delta T simply equals to 2 delta X divided by A and then square root. I'm just solving delta T from here. This is square here, okay? So plugging numbers, you have 2 times 20.4 meter divided by A, which is 9.8 meter per second squared. Okay. Now, if you plug in numbers, you have 40.8 divided by 9.8, okay? So you got 4.116, 4.16, yeah. Well, this is that right? No, there's something wrong here. Hold on. Delta X is 20.4, 20.4, okay. There's something wrong, sorry. 20.4, okay, 1/2 A squared. Oh, I'm sorry, I need to square that. I need to take the square root of this. So square root of 4.46, 4.16, okay. Okay, I got 2.04, okay. Okay, so it's good, okay. So it's the same as okay, so we got this part. This is the time interval it takes to go down, okay. If you add this number to the previous number, you got 4.08. So that's another way to solve the same problem, okay. Now, what I want to, what I kind of hope you guys to see from this problem is, see, the formulas are always given like this, but in order to use it right, you need to know, you know, what is VI, what is VF, what is A, what is delta T, right? It really depends on what kind of motion you're talking about, okay? See, when you talk about this part of motion, this thing goes up, versus this motion here, go up and coming back, versus this part here going down, right? For these different motions, VI and VF are defined differently. You know, you have to choose the right number to plug in. So that's why I'm saying that you need to understand the meaning of those formulas. You need to understand the physics process that you're looking at, okay? And then you can use plug in right numbers for these quantities. Otherwise, it won't work, okay? Any questions so far? Okay, good. Okay, now let's do the last two, okay? The time to go to the ground. So by that time, what I understand is it goes from here, okay, from the initial position all the way to the ground. So you need to figure out this time. Again, there are two ways to do that. One is to figure out the whole time. The other one is to figure out the time to start from here to here, because we already know the time for this part, right? So yeah, do this part here. And then also find out v at t equal to 5 seconds, okay? Do this last two parts as an exercise, okay? Okay, so let's go back to the problem. So let's start from part D, time to go to the ground, okay? So again, okay, dang it, I run out of the page. So I need to get another page. I don't know where, but hopefully. There's a problem with this file. It's not easy to add pages to it, okay? So I got a different new page at the first one. Okay, that's fine. So again, the last one, I mean, the part D here is we're interested in the time it takes to go all the way from here to the ground, right? And again, we know this 50. This is 50. For some reason, my laptop, I mean, my 50 meter, okay? And then this is 20 meter per second. I don't know why it's responding slow. Okay, so we know this two information, right? So let's consider the whole motion, just so meaning going from here all the way to here, right? Let's look at this motion, see what we know about this motion. Well, certainly we know VI, right? VI is 20 meter per second, okay? We also know the acceleration, which is negative 9.8 meter per second squared, okay? Well, the third piece of information we know here is this thing here, which is the displacement, okay? Because this is your initial position and final position. But notice that because the definition of our positive direction, the displacement here is negative, okay? So it's negative 15 meter, okay? Remember, displacement defined as final position minus initial. So that's negative 50 here, okay? So we know this three pieces of information, okay? Now, this is the original problem, right? Before I modify. So if you look at the formulas we have here, given VI, A, and delta X, and we want to find delta T, what formula should we use? It's actually this formula here, okay? It has exactly the four quantities. There's one unknown and then three pieces of information we know. So we should use this formula here to get the get this part. However, there is a problem. Okay, so we use this formula here. You see we have a quadratic equation to solve. Okay, so this is a negative 50 meter. This is a 20 meter per second times delta T plus, okay, minus like 1/2 9.8. That's the 4.9. So you have a quadratic term. I mean, and then you have three terms: quadratic, linear, and constant. So to solve this equation, you need to know the quadratic formula, which we didn't really talk about as we didn't review as our part of algebra. And some of you may know this from your linear algebra. I mean, sorry, college algebra class. Some of you may already forget. As I said, I don't want to require too much from you guys. So let's do not do this. Okay, I will take a different approach. So in the test, we're not gonna have a problem with quadratic formula. You have to use quadratic formula. Okay? So what else can we do? Now, given the other formulas here, with those three pieces of information, if we cannot figure out delta T directly, we can figure out VF. Okay, so if you look at this formula here, we have, see, we can figure out VF from the first formula, and then after we figure out VF, we can use the second formula to figure out delta T, right? So then we don't need to use this third formula. So sorry, we can figure out VF from the last formula because we don't know delta T, so we have to use the last formula here. So what we can do here is using the last formula here, we have delta X equals to VF squared minus VI squared divided by 2A. That means VF equals to 2A delta X plus VI squared and then square root, okay? But notice because VF squared equals this, so strictly speaking, you have two possibilities. You can get a positive or negative out of the square root, okay? So, and this we can solve, okay? We can plug in numbers here. to get 2 times negative 9.8 meter per second squared times negative 50 meter plus VI squared, which is 20 meter per second squared, okay? Again, notice the two minus signs are both important. They cancel each other out, so you have a positive number. So if you do this calculation, you get plus minus of 37.15 meter per second, okay? So the unit here, meter per second squared, is square root of meter per second. So it's this same thing here. So, well, out of these two rules, we need to choose the negative one because at this point, this object is going down, okay? So VF equals to negative 37.15. That's what I gave you so that it's easier for you to solve for delta T. Well, you can figure out by yourself, but it's better to let you do that one thing. Well, some of you may say, okay, what about, I think VF, we already know VF, it should be 0, okay? Because when it hits the ground, the velocity goes 0. However, that's totally wrong, okay? Because the motion we're talking about is the free fall motion when something is in the air, okay? So the final velocity we refer to here is not the velocity right after it hits the ground. It's the velocity right before it hits the ground. It's a very big velocity, okay? And that exactly because the velocity is big, it causes all the damage. So you don't want to jump out of a building of 10 floors or something, you know, or throw anything, like drop off your phone from the same height because it's going to be a huge final velocity here right before it hits the ground. It's going to make all the damage for you, right? So VF is not 0. It's a large number like we're showing here, okay? Now, if you know this, you could use this formula here. You could use all kind of formulas. For example, you could use this formula to solve for your delta T, okay? Or you could use this formula. Either way, okay? Any one of these two formulas, okay? Say, for example, we use this formula, okay? You have delta T equals to VF minus VI divided by A. So you have negative 37.15 meter per second minus 20 meter per second divided by negative 9.8 meter per second squared, okay? As you know, again, all these signs are critical. If you mess up one of these, for example, if you choose positive, you got a way smaller number than you should, okay? And then not only that, you're gonna get a negative delta T, which is totally wrong. So it has to be, this is negative because it's going down. The VF here is going down. Okay, so if you do this calculation, you got a number like 5.83 meter, second, okay. Okay, now you can do let's do the last one then, okay. The last one asks you the velocity when t equal to 5 seconds, okay. Now, again, you're looking at a little bit different motion. The motion you're looking at right now is this thing goes up and then goes back and then somewhere, it stops somewhere here, right? This is your final velocity. You want to figure out that, okay. And notice it takes 5.83 seconds to hit the ground. So for 5 seconds, it's still in the air, okay. Now, if I ask you to find out the velocity at delta t equal to 6 seconds or something, it'd be easy because after that time, it's already hitting the ground. So velocity has to be 0, right? But it asks you something before that. So it's still in the air. So how do we do this? Now, well, because we know bunch of quantities, we still know these two are like VI and A. These are always there. So VI equals to 20 meter per second and A equals to negative 9.8 meter per second squared. So with these three pieces of information, the easiest one to use is this one, okay? So let's use that one. So VF equals to VI plus A delta T, okay? And then VI equals to 20 meter per second. A equals negative 9.8 meter per second squared, and delta T is 5, that's given, right? So plugging all this together, so you have 9.8 times 5 is 49, okay? So together you have negative 29 meter per second. Notice you got a negative number here. It's consistent with the units, I mean, sign and everything here. So basically that means at t equal to 5 seconds, this thing's already going down, okay? As it should be, okay? Because as we know, it takes like only two something second for it to reach the top. So after the 2 seconds is always down. So it should be negative, okay, as we get from here, okay? Does that make sense to you guys? Okay, I think this problem is really a good problem. Try to go back and study this problem carefully. And then all these 5 parts, you know, with all this, everything you need to be careful about, you know, how to set up a coordinate system and what motion you look at specifically, it determines your VI, VF, you know, and delta X and everything. They're all means different things when you look at different motions, okay? And then pay attention to the signs and everything. So it may look hard for some of you guys, but after practicing on it and then do the homework, you'll feel much better, okay? So so we're done with chapter 2 here, okay?